Hello, my name is Gary Buller, Technical Team Lead at Print City, and in this video we are going to talk about the 3D printing process from redesign to manufacture. By the end of this video you will have an understanding of the 3D print process and how to better design for additive manufacturing. We'll touch on the 3D print process, design for additive manufacturing and rules for FDM technologies, and finally the slicing and preparation of your 3D print. We will start with the 3D print process. Here we see a typical 3D printing process from start to finish. Stage 1 is where we model the part, preferably with the technology, process and material in mind. This is known as design for additive. Once this is complete, we move on to the next stage. Stage 2 is where we export the part as an STL file and import it into the slicing software to prepare for 3D print. Here we orientate and scale the part, select settings such as layer height, infill and nozzle size before slicing it. The slicing software cuts the part into hundreds of virtual layers and exports as a G-code file. G-code is a language the 3D printer can understand. Stage 3 is the start of the 3D print. We send the G-code to the 3D printer and observe the first few layers, ensuring the technology is extruding correctly and the print is adhering successfully with the print bed. In stage 4, the print is emerged, layer upon layer. Once complete, we remove the part, remove any support material and post-process before we have the complete object we see in stage 5. We've already taken a look at what FDM technology is and how it works in previous videos. However, it is useful to know there are two types of FDM printers, direct driven and Bowden driven. In direct drive printers, the gears which feed the filament through the nozzle are located in the head of the printer. This means more control over the filament path, more precise retractions, and it is easier to change material mid-print. In Bowden-driven printers, we can expect slightly quicker print speeds. Filaments are not as exposed to the atmosphere, and it is simpler to load. Direct drive printers work better with flexible materials such as TPU or Flex 45, whereas Bowden-driven technologies are perhaps more suited to hygroscopic filaments like nylon. We also need to consider materials before we print our part for repair. Although there are hundreds of polymers to choose from, including composites, they generally fall into the 6 base polymers. PLA prints well with good layer adhesion and visual quality. ABS is very heat resistant. PET combines good overall durability with ease of print. It can also withstand dampness. Nylon is a light material with good flexibility and impact resistance. TPU is incredibly flexible and resistant to impact, but difficult to print. And PC is both heat resistant and durable. The properties of the part will determine the material chosen. How will the part be installed? Under what conditions? What work will the part undertake? Selecting the correct material will greatly increase the success of the final print once installed. Post-processing requirements are also a big consideration. Although we do this at the end of the 3D print process, it is well worth considering before we even sit down to design the part. Some questions we might ask ourselves include: how many support structures will we need to remove? Can we reduce these in our design or by orientation of the part, or a combination of both? Might we need to stand away any imperfections, particularly where the part has been in contact with the support structures? How important is surface quality? Will we need to fill in any gaps or polish the part either chemically or through vigorous sanding? Have you designed the part to be assembled? Are all your tolerances correct? Are you going to glue the part or screw it together? How long will assembly take? Do you wish to paint the final part? If so, what is the best colour or material for that? We are now going to take a look at design for additive manufacturing, specifically design for fused deposition modelling or FDM prints. Design for additive manufacturing is a subset of manufacturing where we adjust the way we design in order to optimise the part additively for 3D print. This could mean reduction of material, including support, an increase in yield by reducing time or quantity per bed, or optimising the shape of the part through processes such as amalgamation or generative design. A well-optimised design simplifies and streamlines production, reduces print time, reduces print failures, and ensures the success of a 3D print. When printing specifically for fused deposition modelling, there are several design decisions which need to be considered for your part. Each FDM printer has its own specific capabilities, and it is always worth reading the manufacturer's design guide to ascertain these tolerances. That said, as a rule of thumb, the dimensional tolerance of FDM machines is 0.5mm. Shrinkage or warping is between 0.2 and 1% depending on the material you use. The maximum angle before support materials required is usually 45 degrees. The maximum emboss or deboss depth is 0.6mm depending on layer height, in this case 0.2mm. Thinnest wall width is usually 2 passes of the nozzle, i.e. 0.8mm for a 0.4 nozzle diameter. When printing using FDM, it is worth knowing that we are limited by the nozzle diameter. Thinnest features must be designed for the nozzle you are using, so if you have a 0.4mm nozzle, then a 0.4mm will be the thinnest you can go. Design wall thicknesses in multiples of your nozzle diameter to ensure accuracy. For structural parts, use thicker walls to increase strength. Increasing infill will not necessarily make a difference. Design around layer orientation for successful structural parts. No tension and bending forces applied to the part, and orientate accordingly for the best results. Ideally, a part designed specifically for FDM printing should need little or no support when orientated correctly. Supports are inefficient, they increase print time, increase material use, and can affect the likelihood of print failures. When designing for FDM, we do our best to keep angles lower than 45 degrees. When designing for FDM, think YHT. The Y shape or letter can print without support because the overhangs are 45 degrees or less. This is ideal. The H shape or letter H will print without support if the bridge of the H is less than 5mm, but generally speaking may require a minimum amount of support. And finally, the T shape is the most wasteful because it requires almost as much support material as the part itself. That said, if we think outside the box, we can orientate all 3 letters to print without support by simply lying them on their backs. Alternatively, parts which may require a lot of support can be split into separate components. Think outside the box when it comes to designing angles into your parts. FDM technology does not print holes very well. Because of the layer upon layer nature of the technology, vertical face holes are often slightly flat on the top layer, giving them a squashed look and reducing their dimensional accuracy. A circular hole may also require support, which can be difficult or tedious to remove. One way to get around this is by changing the hole to a teardrop or diamond shape, as we see in these illustrations. As discussed, a 45-degree overhang can be printed without support. The gradually supported angles also mean the hole is more likely to be dimensionally accurate rather than sagging under gravity. So what is slicing software, and how do we prepare a CAD file for 3D print? Slicing software converts an STL file exported from CAD into G-code, slicing the part into hundreds of layers and converting it into a language the 3D printer can understand. The resulting G-code instructs the 3D printer how to operate, dictating movements, material flow and temperatures. Each setting change informs the end result and impacts the finished print. As a minimum, slicing software enables us to rescale position and orientate a part. It also enables us to select and increase the density of infill and support and alter printer material settings. Slicing software may also encourage variety and experimentation with additional features which enrich, optimize or improve your part. Here we have the typical workflow of a piece of slicing software, in this case Cura. First we select the correct printer. G-code differs depending on which technology we are sending the print to. Then we select the material we are using and the nozzle or core size. This ensures the nozzles heat to the correct temperature and extrude at the right speed. Finally, we select our print settings. These settings include the height of each layer. This is essentially the vertical layer resolution of your 3D print. The smaller the layer height, the higher the resolution. The type and percentage of infill. Infill is the structure and shape of a material within the solid part. Infill can be simple geometric shapes or patterns. The higher the percentage of infill, the denser the interior of the print and the more material is used. It's also worth mentioning that infill can determine the strength or flexibility of a part depending on the pattern used. The build plate adhesion, or the way the print sticks to the print bed. Once we are happy with the settings, we can drop our part into the slicing space. We can then orientate the part, scale it and rotate it. Finally, we slice the part, preview to ensure we are happy with the results, and then send the G-code to print. When printing, we observe the first few layers to ensure the print is extruding correctly to the print bed. So there we have it, from redesign to manufacture, an overview of the FDM printing process from design for additive through to slicing, printing and also post-process. Thank you very much for watching this video, and I look forward to talking with you next time.